Hello friends, welcome back to the channel. In this video, I thought we would talk a little bit about what Natalie is and how Natalie works and where Natalie came from. I've had some people ask over the last few months how everything is put together, and our friend Ryan asked in Discord a couple days ago if we could make a video about it. So here we are. We're going to talk a little bit about Natalie. No coding today, I don't think. Just an overview. So anyone not aware, Natalie is a Ruby implementation that I've been working on for over a year. But some other folks have come along in 2021 and have been lending a huge hand. And you can see that from our little graph down here of our Ruby spec suite that we have the benefit of using because the Ruby community is fantastic and shares all of this work with everyone. But being able to run the Ruby spec suite on Natalie and to see our progress over time, and we only started running this like a couple months ago, or maybe not even, maybe like a month and a half ago. But you can see already that the erroring tests are going down, the green line of successful tests is going up, and the yellow line of failing tests is going down, except for this little glitch right here. But for the most part, we're trending in the right direction. We still have a long way to go to be a real Ruby, but already we can run real Ruby scripts as long as you don't need a Ruby gem or external library. Then there's a whole lot of Ruby that actually works. And I'm not going to go over everything, but you know, like ranges and string interpolation, you know, classes and accessors, adder readers and writers, blocks, obviously. No more about that. Let's just get right into talking about how Natalie works and what it's all about. I have to say, I am not a compiler writer. This is only my second compiler, and I feel, and I don't have any formal training. I'm not really well read on writing compilers. So I don't want to say this is a good way to write a compiler, but it works. And I kind of consider it the newbie way to write a compiler. Essentially, the overview is that we parse Ruby code into a tree, an AST, an abstract syntax tree. We walk the tree and produce C++ code as a string, like a really, really big string. We write it to a temporary file, and then we run that through GCC or clang to produce a binary. And what that really looks like is, if I show you the hello Ruby script, it's just a puts hello world. And if I do this, bin Natalie examples hello.rb, a lot of what I just told you is sort of hidden away. You don't see the temporary file get created, but it gets created in /temp. I think it even gets deleted, so you can't even see it. So what I can kind of approximate that is if I do -c hello, and I tell it to compile the binary right here, instead of compiling it as a temporary file and running it, I can do like this. And you can see how much time is taken compiling. It's not fast yet. A lot of that time is spent in GCC on my machine. But if we run the hello binary, it's quite fast, you can see. That just takes, 0.005. So I'll kind of go over all the different steps in between there. But you can see that the hello file is its own 64-bit ELF binary. Let's show the very first step, the AST. If I run bin Natalie --AST over the hello script, then it's going to show you a very, very short and small and tiny tree. And you can think of these as arrays, sort of like if you're familiar with Lisp, this is nested lists, and that's how we represent the parsed tree, is just nested lists. And so if we go from the inside out, there's a string hello world, and one layer out from that is a call, and the call is to puts. This nil is here because if you have an AST where you say foo.bar, then the well, that's a bad example. That's a bad example. Let's do a number. Then in place of that nil would be the receiver of that message or that method call. But since puts is just by itself, it's nil here. And then that's all wrapped in a block. And so if you had, you know, 2 or 3 expressions, then those would be wrapped in a block, and each one is its own expression inside of that block. And this is not a Ruby block. This is just a block of code. But that's what the AST kind of looks like. And I can show you with a larger, like the Fibonacci example code. It kind of looks neat how it's, gets indented when we pretty print it. And it's fairly readable. You can kind of pick out. So if I show you the Fibonacci code here, you can kind of pick out what comes from where. That's the parser part of everything. And then we have a set of passes. So we have compiler RB, which sort of glues them all together. I'm not going to go over all of this, obviously, because it's grown over a lot of many months, 300 lines of code. But I will show you the passes. So pass 1 takes the AST, and this is using a thing called the sex processor. There it is. This is based on the sex processor from a Ruby gem, but I am in the process of rewriting our own version of it. So but this is what it does is it just walks the tree of the AST, kind of dives down into the nodes, walking down deeper and deeper. And if it finds a method called process underscore for that node, then it runs it. And whatever this returns gets replaced into the tree. So if there was an alias node, then it gets replaced with this. That's probably not a great example. Process array returns. Yeah, let's do that. I'll show you how that works. If I do E and 1, 2, 3, then that's not going to print anything because I didn't tell it to print anything. But if I pass AST, then it's going to show you the abstract syntax tree. It's an array with a literal 1 and a literal 2 and a literal 3. So pretty easy to understand. If instead of AST I pass debug pass 1, it will show you what is the result of our internal representation of the AST, our manipulated AST, after pass 1 is complete. So we have these little debug flags where we can see what is produced. And so what pass 1 created from this is this. It declared an array. This is a unique name, and the way we do that is we just append a unique number on the end. We increment a number, so not super fancy, but it works. We create a new array value, which this gets translated into C++ a little bit down the line. I'll show you that soon. And then for every item in the array, we call push with the array as the first argument and the integer 1, integer 2, integer 3 as the second argument. And then from all of that, it is wrapped in a block, and the last expression of a block is what is returned. So for this block, what is returned is array 1, which we created here. I hope that makes sense. I've been looking at this for many months, and it makes sense to me. It's like, yeah, it makes perfect sense, but I don't know if I explained that very well. But that's what is produced from pass 1, and we'll run this through pass 2. I don't think anything changes on arrays on pass 2. Oh, a little bit. So we have var alloc 0. That's just for local variable allocation. Trying to think of an example. Let's come back. I'll go through all the passes with just arrays, with just this array first to see. Let's see, nothing changed there. And then pass 4. Right, we don't have pass 4. We do have the final code, which I can just do with -d like this. This is the final string, and you're like, whoa, how did you go from here to all of this? It's not as bad as you think. Most of this is static code that doesn't really change a lot for the most part. It's sort of a template. Let me go show you that. If I go to main CPP, this is the template that we insert C++ code into. This is some stuff that we declare, which is right here, all of this stuff. This is some stuff we initialize, and that is... Where is that? Where is that? Oh, it's right here. All of these initializers get run right here. Right here. And then this is the eval init. So what goes there? If I go down to eval, we set a few things. Yeah, we set this global variable. And I guess that's it. I think at one point I thought there'd be more there, but there's only that one thing. This code just gets inserted verbatim. Okay, and then here is the meat. If I go down, you'll see that was a try block, right? So try and catch. If I show you the same part, here's the try, here's the catch. So this code got inserted. How much of that code got inserted? Everything up to run exit handlers. So this is the code that was produced from this. So it's not that bad. It's mostly understandable, I think. Let's go line by line. I don't know. Fast forward if it's boring or obvious. I don't know how much detail. Declare array1 new array value. Pretty much does what it says. There is some intermediate temporary variables here because I'm not very good at producing efficient C++ programmatically. So this is a little bit silly that we do new2 array1 equals new2. I'm really relying on GCC to optimize all that away for me. I could do a better job, but it's just not been an issue until now. I think at some point I'll come along and go, we don't need to do that. It would be a little more readable if it was one line. But, and that's in pass 4 that it produces these extra variables. So if you want to work on that and PR a change, I would accept that. And then, I went too far. Boop, 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 boop. So each one of these lines turns into how many lines of code? 1 or 2. We set the source file name and line number on the environment. The environment's sort of like a stack frame, but we set that all over the place so that our backtraces get the right string, the right location and line number. And then this creates a new integer for the number 1. And then we push it onto the array. So these 2 lines came from this line. And I think you can kind of see how this these nested lists get turned into C++ code. It's pretty straightforward, I think. But that's the meat of what Natalie is doing. It is just, transforming incrementally the AST into something that looks more and more like C++. And at the very last step, we turn it into a string and insert it into this template, this big template. And then the last step is we run GCC or clang. And the way that I do that is right here, temp file. Let's look for temp file. So we create a temp file, we write to the file, we close the file, then somewhere, here is the compiler command. So cc gets turned into either the cxx environment variable or C++. So it's going to use whatever's on your system, whatever you've configured as your C++ compiler. We got some build flags. We run it with position independent code, so our REPL works. I'm not going to get into that. Our include paths, where we want it to write out to. We're saying that it's C++ 17. We'll probably switch that to 20 soon enough. We have some library paths. I believe those are just the build directory right now. We include the Natalie library, which gets compiled by our rake file, and some linker flags, and we join all that together with a space and we run it, and that's it. So we run this command just by calling the backticks. And once that's done, we delete the temporary C++ file, and somewhere we'll actually run it. Where does that happen? Where does that happen? So I guess it's in bin Natalie. We compile C2 binary, edit compile. Nope, that's not it. Compiler, show assembly, compiler. I don't actually remember where this happens because I don't look at this very much, but compile and run. Let's go look at that. It looks like this does some of what I just showed you as a duplication. Why do we do it twice? I don't know. I feel like I just showed you code in a different file that does the same thing. So there might be some duplicate code there. Yeah, probably because we have all kinds of flags we need to support. There's cool stuff here. So we have the debug flag, which has a bunch of undocumented stuff. So if I run hello world, and I run I pass -d gdb, then it's going to compile it and run it with gdb. So I can type run here, can get, oh, well, there's no error, but if there was, I could type, I could get a backtrace, and this is super handy for debugging problems. I wonder if I could make it. Could I make it produce an error? No, I can't, because that's an error that we catch and raise inside of Ruby. So yeah, I don't know. I can't think of a way really easily to produce a backtrace, but that's okay. And that's it. I don't know. That's the noob way to write a compiler. I don't know if that helps anyone or gives you an idea of how I did it. This, again, is probably not the best way to write a compiler. I think in 2021, if you were going to make a respectable compiler, you would use LLVM and do what everyone else is doing. I didn't feel comfortable doing that, so I did it this way because I've seen some JITs. There is the Ruby JIT that's built in. What do they call that? I've MJIT or YJIT or something like that. It does this sort of thing where it produces a string of C code and then it writes it to a file and then it runs GCC or clang on that. So I thought, well, if they're doing it, I can do it. So it's not totally crazy to do this. It's just, there are some obvious downsides of shelling out to a separate program to do this sort of thing. LLVM integration is more tight into your program. So that's what I've been looking into. And I think my previous video was a little bit about LLVM, and I've got another video coming soon about LLVM. So I'm going to be learning that next and trying to hopefully someday make this a better process. Let's see. Is there anything else I should go over? The C++ code runtime stuff is pretty boring, I think. If I show you sort of this, Ruby is a dynamically typed language, which in terms of C++ means that we have a root value object class that everything else inherits from. We have our own garbage collector. I have a video about that if you want to go look at that. So we inherit from cell, and that's provided by the garbage collector, but everything else inherits from value. So if I look at string value, it inherits from value. And if I look at integer value, then it inherits from value, and so on and so forth. So every object in the runtime inherits from value pretty much. Every object that the user can really work with. And that is how the dynamically typed part of Ruby is implemented in C++. And so when you're compiling code, I mean, it really just comes down to changing what you get from Ruby and turning it into C++. So let's just go over one little example. Let's go over and. Yeah, why not? So if I do bin Natalie E1, 1 and 2. In Ruby, that is just going to say, well, this is truthy, so the value of this expression is 2 because this one was truthy. If I did false here, then the value of this would be false. Or if I did nil, then it would be nil. But pretty simple stuff. It also is the same as this. We'll just trust me, we'll say that it's the same. So if I show you the AST for that, it is just and 1 and a 2. A 1 and a 2. Then I show you what is produced by pass 1. It's a little more involved, right? We have to turn this into C++ code because this is not the same in C++. So one way we do that, or the way we do that, is to declare the left-hand side to be a 1, and then we basically create an if statement. So let me go all the way to C++ so you can kind of see what's happening here. So the left-hand side is the integer 1, and I know there's some temporary variables here. If that's truthy, then we set the value of if to that value. If it's not truthy, then we set the value of if to the... Oh, sorry, I said that wrong. If it is truthy, then we set the if value to the right side of the and otherwise we set it to the left side. Okay. So that's what it looks like in C++, right? That's how I was able to create the semantics of the Ruby and keyword in C++ was to turn it into an if. So hopefully now we can talk about this code and it hopefully makes sense because I needed this to be an AST, so this is a C if. I need a better word for that, but that's it's basically saying like it's an if that's been processed, and we need to turn it into C code. So it is, you know, the if, and then the condition, and then the truth value of if it's truth, if it's true, and then the last argument is if it's false. That's the value. Does it make sense? I don't know. Does it make sense? What's something else we can go over? What's something else? I mean, that's what this process and is doing. It's saying it's getting the left-hand side of the S expression, and the right-hand side, we're just ignoring. This underscore is just and, so we don't care about that. So we're just ignoring that. We're processing the right-hand side because it might be an expression. So what if it was x equals 2? Then we have to process it because it's its own expression, which might be a variable set of x to 2. So we process that through the same pass, and we create a temporary variable. That's what this little helper does. And then we call declare, setting the value of the left-hand side to that temporary variable. And then we produce this if expression with how we want it to write the code. Hopefully that makes sense. I did want to show you, there's actually, I just remembered, there's a couple of other passes called pass1b and pass1r. These are like little teeny tiny passes, only 100 lines of code. All it does is this one converts break into a return or a throw local jump error. So I had a lot of trouble getting my brain to find an abstraction that worked. And so these compiler passes really works in terms of separating out the different state changes, and having smaller passes that do a lot less actually helps. And I wish I would. So I guess that would be my tip. If you're writing a compiler this way with multiple passes like this, make them small. Don't, pass one in the compiler is 800 lines of code. It's a little big. I wish. I think at some point I'd like to go through and just identify some other things that are that could be put in their own pass. Like rescue is a little beefy. It's a little big. But anyway, pass1b does that, converts breaks into returns. Pass1r, come on. There we go. Pass1r converts a return into a throw local jump error. So these two are similar, but they do very different things, different semantics between break and return. And so having them separated helps a lot. So I know that if I'm fixing a bug in return, then I go to this file. If I'm fixing a bug in break, I go to that file. And it's nice. So yeah, separate out your passes as much as possible. Makes things a lot nicer. So pass2 is computes captured versus local only variables. So, I mean, I don't know how much you know about closures, but hopefully if you're watching this channel, you know what a closure is. In Ruby, a closure is something like, if I have, let's say this is a closure, it's basically going to be a proc. Let's set a variable first. Let's say x equals 100. And my closure is going to be a proc that just returns that, that variable. So now C is a closure around this. So C needs to carry along with it the reference to this variable. It can't lose track of it. So this compiler pass, just goes through statically all the different layers of AST and figures out if it's referencing a new variable that's local to that scope or a variable that was declared in a higher scope. And that's a lot of fun. Actually, I had a ton of fun writing this and figuring out how this works. How many lines? 150 lines. Not bad, not too hard. It just has to know the semantics of the language. So in Ruby, if I say, let's say y equals 100, and then I have a method called get y, and I try to return y, it doesn't work because the y in this scope is not this y, because in Ruby, the semantics of Ruby, this is not visible inside of the method. Why? That's just how Matt's made it. I think it's nice because it reduces a lot of accidental errors of seeing variables outside of your scope. So if you wanted to reference that, you'd have to make it an instance variable. So you could say at y equals 100, def get y is just return that instance variable, and that actually works. But so that's why there's these different like sort of versions for if there's a method, then it sort of creates a new barrier to variables defined outside of that method, and so we get to sort of reset our scope. But if we have a block, let's say z equals 100, and we what's a method that takes a block? I'll say each, this is going to be my block. Let's just return Z. This block scope can close over the variables defined here. So blocks behave different than methods. And so that's what this pass sort of keeps track of and does the work there. And that was a lot of fun to write. Like I've already said, pass 3. Oh my goodness, it's very small. It's 31 lines of code. Replace non-capture variable references with local C++ variables. This was just an optimization. I honestly don't remember exactly what I was thinking. Let's go play with it. Bin Natalie. So if I say x equals 1 and then print x and I debug that, then what I get out is right here we're setting x1 equals this. You have to look at both lines, right? So here's the integer 1 and we're setting it to x1, and then we're passing x1 in as the arguments to the p method. And so you notice that this is just a regular C++ variable, just a regular old variable. And we do first set it to nil first, but yeah, I don't really remember why we do that. Why do we set it to nil? Why do we set it to nil first? Yeah, I don't know. That seems like something that could go away. Yeah. Well, anyway, moving right along. So this is a regular C++ variable, but and that is thanks to this compiler pass. I think if I turned it off, how do I do that? If I turn it off, pass 3, let's just comment that out and run it again. Okay, forget that. It doesn't work. I'll have to come up with a better example. So what if I call .call? Does that produce 1? It does. And if I debug it, so yeah, I should mention I created a closure here. So now I can't use a regular C++ variable because it's special. It has to be treated completely special. So what we're doing, this code gets completely rewritten, and now we are setting a variable called x on the environment, the stack frame I talked about earlier, because it needs to be available outside of this scope. That block that I wrote is up here. It's a separate C++ function that gets called when the block is run, and it has to call env outer variable get x. So that's what pass 3 does. This actually is pretty cool that it's only 31 lines of code, and it is able to swap back and forth between what you saw earlier with a regular C++ variable and this monstrosity of having to set it on the stack frame. So that's pretty cool. Okay, pass 4, and pass 4 is the biggie. It's the big bad boy. It turns the nested lists of AST into strings. And just to give you an example of what that looks like, I'm going to try to skip some of the weird ones. Let's look at that cif one. Remember that cif, which was produced by 1 and 2, pass 1. Right here, cif, if the left-hand side is truthy, then return the right-hand side, otherwise return the left-hand side. That gets turned into a string using this code. And it's as gross as you think it is. A lot of the string manipulation code I can't say I'm super proud of, but we just have an array and we're appending little bits of string onto the array, and it's just string interpolation, and you can kind of see the if. Here's the if here, And here's the else, if there is a false body. If there's not, we just skip the whole else entirely. And then here's the closing brace. And then the result name is a temporary variable that we created called if. So yeah, and it's full of that stuff. It's 700 lines of just string manipulation. Did I mention this might not be the best way to write a compiler? It's the way I came up with to do it. There's probably a better way. I think a real, quote, real internal representation that was a little more abstract would maybe make this better. But yeah, it is what it is. It's worked for many months now, and it's allowed us to get really far with Natalie and the implementation and how, and a lot of the specs are passing, the Ruby spec suite. Let's go back here and end on this note, talking about the Ruby spec suite. Our friend Richard has implemented something that's pretty cool. We now keep track of which specs are passing and which are failing. So you can actually drill down into like array, and you can see that there's some issues with clone. If I recall, we didn't really implement clone. We kind of stubbed it out and said, we'll do it later. But you can see that there are a ton of things passing. But yeah, we've managed to get really far with the compiler as it is, and that has given me a lot of hope that you can scaffold your way up. There's I wanted to mention that the parser gem that we used, I didn't want to deal with parsing in the beginning, so definitely use whatever you can to build your way up. And it's sort of I wish I had like a good analogy, but like I feel like we sort of like prop this up with a broomstick, and then we build up a good foundation over here. And now I'm coming back to the parser side that's propped up with the broomstick and building out our own parser in C++. And it's fast. It's really, really fast. It's not done yet. But once the parser is more done, then you'll kind of see this side over here lacking. And so there are things that we've propped up. I mean, one classic example I think is, let's see if I can find it, def pp. I needed a pretty print method and I didn't want to implement it. So here's a big fix me. And this is the nastiest hack. I write a temporary file. So, what gets written in. So if I call pp, let's say I call pp with an array of 1, 2, 3, like that. What gets written to this temporary file is just the string representation of that. And then I shell out to Ruby to produce a pretty printed version. And this is what I'm talking about. There are things like this in Natalie that are scaffolded to allow us to get work done. And we're going to come back and rewrite that. And I feel like that is an important part of writing any language interpreter, compiler, or whatever, is not being afraid to use duct tape or sellotape or whatever to hold something together while you work on this thing over here. And then you get to come back and work on this other thing that you propped up with the broomstick. Okay, so not the best analogy, but I hope that makes a little bit of sense. I mean, that's embarrassing. That's really embarrassing that we're shelling out to Ruby to pretty print stuff. But, you gotta do what you gotta do. That's it. That is the longest explanation of how Natalie works that I've ever spoken out loud. Forgive me if it wasn't super riveting. I will have a video about LLVM coming soon, so hopefully that'll be a little bit more interesting. I do appreciate you hanging out. Hope that you learned something, and I will see you in the next video. Bye.